particulate matter settling through water and settling on the bottom of the lake or the ocean, it's going to be the case that the first rocks that are formed are the ones that are on the bottom, because they're the ones that have the first mud or dirt falls onto. Okay? So this is a very simple principle, but necessary if you're going to date, come up with a geological timescale. I also mentioned too that most of the time when you look at a column of rocks like this, most of the time is in the bedding planes between the rocks. As I say, these rocks are usually formed, at least in some environments, over a short period of time, and then you have a long period where you don't have any deposition, and then another bit of rock to deposit. It's the 1,000-year flood that does a lot of the deposition of rocks. Another principle which is really easy is that the rocks were originally horizontal in nature, and that if you see them tilted, the tilting must have occurred after the rocks were formed. If you go out along Claremont Boulevard, I believe it is, I always forget if it's Claremont Avenue or Claremont Boulevard, but the road that goes behind the Claremont Hotel up to Grizzly Peak, take a look at the exposed rocks along there. There's at least some pretty spectacular exposed rocks which give you an idea of how geologically active our area really has been, where you see layers of rocks which are twisted and curved. It's just remarkable. Okay? Well, the point here is that the rocks were originally formed horizontally, and that twisting of the rocks, the deformation of the rocks occurred after they were formed. And you say, well, that's obvious, but it's very simple, obvious things like this that allow you to come up with a very complicated timescale like this, piece together how old which rock is older than which other rock, which event occurred before another event. Another principle people use is that if you find a red rock that you have with particular characteristics in one area, and you find the same formation or something that looks like the same formation 10, 20 miles away, that originally those rocks were contiguous, as to say that they were one rock unit, and that if they are not contiguous anymore, that the erosion occurred after they were formed. Cross-cutting relationships is another obvious one. If you see faulting in rocks, which is something easy to find around this area, the fault occurred after the event that caused the fault, and the fault in itself occurred after the rocks were formed. That's got to be obvious. Inclusions are little bits of rocks, usually sometimes formed through water action or other mechanisms that are inside of rocks. Those inclusions occurred after the rock itself was formed. Once again, a before and after, which event occurred before the other. And then unconformities are areas of large amounts of missing time. Right? So what you see here, this is called an angular unconformity, but there's actually a lot of history that's gone on here. You see layered rocks that are tilted here, a line, and other layered rocks above it that are horizontal. Right? The sequence of events, according to the different principles I talked about, was originally these rocks were deposited oldest to youngest horizontally. They were tilted, you had erosion, and then you had more sedimentary rocks deposited on top of them horizontally. Right? Think about how much time is involved in forming rocks like this. Not only you have to form the rocks to begin with, you had to tilt them, erode them, and then deposit more rocks on top of them. Okay, so these are some of the very simple principles people use to determine the relative ages of different rocks. Right? And in fact, you could come up with everything I put on the board here except for the numbers with relative age dating. You can do all of it except for the numbers. So for a long time, people said, well, the Permian Triassic must have been a long time ago, but you'd be speculating essentially if you tried to determine how many hundreds of millions of years ago it was. It wasn't until radiometric age dating came around that we were able to determine the absolute ages of rocks. And the basic idea is this, is that there's certain isotopes, certain atoms and isotopes of atoms that decay spontaneously. Right? And when they decay, they decay to another isotope, right? Another atom. Right? So for instance, potassium-40 decays to argon-40. That decay occurs at a constant rate, and that rate can be measured in a laboratory. Okay, that's an important point. You can actually measure the rate at which these different parent isotopes decay to their daughter isotope. And the rate of decay is usually expressed as a half-life. Right? That's the rate. The half-life is a measure of how rapidly you have the parent isotope decaying to the daughter isotope. Okay? Once again, you can measure that rate in the laboratory. The point here is that if you have, this only works on certain types of rocks. You can only date what are called igneous rocks, rocks that form from molten rock, from the cooling of molten rock. But when the rock cools, it essentially sets the clock to zero. Okay? So when the clock is set to zero, you have 100% of your parent isotope embedded in the rock and none of the daughter isotope. Over time, as this decay occurs and the rock becomes older and older, you'll see a larger fraction of the daughter isotope relative to the parent isotope. When the ratio is 1 to 1, that means you've gone one half-life. Okay? So the point here is it's tricky to measure the amount of, it's a technical skill, but it's technology to actually measure the amount of parent and daughter isotope, but you can do it. And you can do it in a very careful and controlled way, which means you can date the rocks. So if you, for instance, have a bunch of sedimentary rock with an ash layer, with more sedimentary rock on top of it, well, you can't date the sedimentary rocks themselves, but you can sure date the ash layer, which means that this rock has to be older than this ash layer, and this rock that's on top of it has to be younger. Right? The remarkable thing is, well, it's not remarkable actually, but it's reassuring, is that when people first started to do this radiometric age dating, you can imagine you'd be able to say, well, that rock really is older than that rock because of the absolute age dating. And that matched what they already thought about the relative ages based on those principles, those very simple principles that I talked about earlier. So it was concordant with and confirmed the earlier relative age dating that we had. Right? But that's just wanted to point out. And of course, some of these, Right, so some of these systems, potassium argon is very good for dating pretty old rocks, but carbon-14, which is right down here, this is used for dating much younger material. Okay, so once you get to 1 million years, carbon-14 type of dating is useless. Okay, it's only used anyways to date organic material. But you can use different systems here, different types of parent-daughter isotope systems to date the age of different rocks. It's pretty cool, I think. So this is just to give you an idea of, I showed the geological timescale on the board. A geologist can do this in a much more detailed way, and even much more detailed than I'm showing you here. This is a geological timescale that you can actually get handed out. They hand these things out at places like the Geological Society of America. But the point here is that even these different periods, here's the Triassic, are divided up further and further. And you can even take this period, or this, age rather, of the Triassic and divide it up further. Okay, so people can actually date the ages of rocks in a very, very fine scale, to the point where you can actually find oil using these methods, right? You can use geology is a very useful field for all sorts of reasons. I might do it on time. Okay, I've got some time. I think I'll just mention briefly that besides dating rocks, you can also determine their relative locations on the surface of the Earth when they formed. This is something you can do with igneous rocks, once again, rocks that form through the cooling of molten rock. And that's because the iron particles in the rocks, as the rock cools, those iron particles align themselves to the Earth's magnetic field. Right? And so you can actually, and then once the rock cools, they're frozen. Right? So the point being that you can actually determine where in that magnetic field the rock was formed. And people have done, using this, they were able to learn a lot about plate tectonics. So for instance, if you go across the mid-Atlantic ridge, you'll see the magnetic field. What you see here is the orientation of the ferrous material in these rocks along the base of the Atlantic Ocean. And I should mention that the magnetic field flips occasionally, right? So in the past, if you had your compass, you would find that the North Pole would flop around and point to the south, which would have been kind of disturbing if you were happening to right away. I think it occurs fairly slowly. But the point is that the magnetic field is flipped, and you can actually measure when it was pointing to the north, when it was flipped. Okay? And so what you're seeing is this is the current magnetic field, and it's flipped, and it's flipped again, and flipped. And you see it's occurring in stripes. Well, these types of this, as an aside, this type of evidence was used to support the idea that the plates on the Earth are moving around. Basically, mid-Atlantic, the plates are spreading apart, and in places like Iceland, you can see that type of activity very clearly. But anyways, they're used to show that, that the floors of the ocean, at least in the mid-Atlantic, are spreading. But it's also used to determine, that's pretty cool, I'll have to show that to you again, to figure out where the continents were in the past. All right, so this is the current orientation of the plates on Earth. But what does it look like in the past? Well, in the past, the continents moved around, right? They didn't move that fast, but they were in different positions. There was a period of time, for instance, when all the continents were together, about 250 million years ago, when they called that supercontinent Pangaea. Okay? And the interesting thing is these past continental configurations have left their mark on the evolutionary history of organisms. As I say, there's many species that are closely related to one another that occurred in the north of Pangaea or the south of Pangaea today, and their distributions look a little bit weird because you find them in South Africa and Australia, for instance, but in the past you have to recognize that they were closely together. So this is plate tectonics has been used in studying the biogeography, as I said, the distribution of living plants and animals. So let me talk a little bit about fossils, since that's what I want to talk about anyways. So fossils are any remnant or evidence of past life. Right? Usually when we think of fossils, we think about something like this. One of my favorite fossils is a trilobite. Right? These guys were scurrying around in the oceans in the Paleozoic. Okay? But they can be of other sorts as well. They can be, of course, preserved material like I showed you, but they can also be traces. They can be tracks. They can be footprints. They can be burrows. They can be scat. Right? So if you've ever heard what does anybody know what a coprolite is? It's preserved poop. Right? But that is evidence of life in the past. Absolutely. And so the past trait, it not only can be the preserved material, but also their traces as well. I think there's an important thing you should recognize about the fossil record. I did talk about in one of my earliest lectures about how the fossil record is imperfect. So when you go to an area that has a lot of fossils and you look at the types of organisms you find represented in the fossils, that is a very biased view of what the environment looked like at that time in the past. It's a biased view. And it's biased because only certain types of organisms really have much of a chance of making their way into the fossil record. It really helps if you have a thick shell, as an example. When you look at mammals, the fossil record of mammals, there are some spectacular examples of very complete preserved skeletons, but most of the fossil record for mammals is in teeth, the hardest part of your body if you think about it. So some evolutionary biologists joke to mammalogists that when they make phylogenies, it's teeth giving rise to teeth, right? Because that's the main thing they see in the fossil record. So it's a biased view of the past, and there are a group of paleontologists who try to understand these biases. They study it's a subfield of paleontology called toponymy. Okay? And they study all the events that occur from the time an organism dies to the time it finds its way into your museum drawer. Okay, what are all the different things that can occur that might bias your view of life from the time the organism dies to the time it's found and put in the paleontologist studies it? And the point here is that when you die, you have organisms either immediately buried. Your best chance of becoming a beautiful fossil is if you're immediately buried in a nice calm environment, so you can decay in peace and your bones can be replaced by minerals. Okay, so when you die, when organisms die, they can be immediately buried. Diagenesis is this process of replacement of bone material by a mineral material, and then you're a great fossil, perhaps. Right? You still have a lot more to go before you find your way into the museum drawer. You have to be exposed, as to say, the rocks have to become exposed and weathered, and then finally you'd be on the surface of the earth again, where you'd be picked up by some lucky paleontologist. The other thing that might happen is you have delayed burial, in which case, if you think about the Serengeti in Africa, what happens? Well, you're a wildebeest that dies, you're sitting there, the hyenas come, they scavenge your carcass, they spread your bones, more wildebeest crunch up your bones as they're walking by. That would be an example of, okay, you're exposed for a while, your skeleton is scattered, maybe eventually at least parts of your skeleton is reburied, and then you get a pretty crummy fossil in your drawer, right, eventually. But these are the types of things that paleontologists try to understand is what types of organisms are preservable, what are the chances of making the fossil record. When you see a group of organisms, what type of organisms will likely not have been represented? As an example, you go out to the yard here, the grass, the freshly planted grass, and dig around, there's a good chance you'll find earthworms. There's not a lot of earthworms in the fossil record. They don't have a lot of parts that are hard enough to become preserved well. There are examples of spectacular localities, there's places where you can find fossils of all sorts, right? They're not a lot of them, but they're very valuable when you find because they have a much better picture of what type of diversity was in that area. Archaeopteryx came from just such a place, a place that actually preserved not only the bones, but even the feather impressions of the bird. All right, so I think I already talked about that. So what types of fossils are out there? Well, there's the micropaleontologists. They're not very small paleontologists, but they're paleontologists that study microfossils. So these are much of the diversity in the oceans is things like diatoms, right? That have single-celled organisms, but they have I believe it's made of silica, a test, small skeleton test. These types of fossils are incredibly useful, not only for determining the very, very finest scale relative ages of rocks. They're used a lot for that, but the fossil record of some of these microfossils can be incredibly complete. They occur in the deep sea where sedimentation occurs at the most constant rate, and where the fossil record approaches the ideal that many people would like. That is to say, you can almost see in every single layer representative fossils and change through time. That's the most ideal situation that you can imagine, and the ideal is approached at least in some groups for these microfossils in the deep sea. Here's examples of invertebrates. On the left, we have a fossil oyster, Griffia, I believe it is. There are places in Texas where you basically can't walk without stepping on these things. And then this is a belemnite. This is the bone of a squid from the Cretaceous. But these are just examples of invertebrate fossils, not particularly spectacular ones, but those are examples of invertebrates. Here's what you probably think of when you think fossils. This is a fossil of a vertebrate. This is at the Field Museum of Natural History in Chicago. This is Sue. This is a very famous litigious dinosaur skeleton. So fossils have given us some insights into the very earliest life on Earth. Okay? And this is, I told you that around 540 million years ago, the fossil record suddenly gets much better because there are more organisms at that time, for whatever reasons, that had hard parts. But the fossil record predates the beginning of the Cambrian by several billion years. Right? And some of the earliest fossils we find are things such as stromatolites. Stromatolites are bacterial gnats. Right? You don't really find a lot of them today, but they're famously known in Shark's Tooth Bay or Shark's Bay or something like that in Australia. Right? So you can actually find them in this hypersaline bay in Australia. These are living stromatolites. But our earliest stromatolites go back billions of years. Okay? Another important point about the fossil record is that it does preserve some transitional forms. Right? I mentioned this earlier in one of the earliest lectures, but I want to mention it again. This is an example we would consider a transitional form. This is Archaeopteryx from that spectacular site in Germany. This is a Jurassic bird. You can see it has feather impressions. People think it could fly through powered flight. But it has a lot of characteristics. That would be a characteristic that definitely is a modern characteristic of birds, having feathers that are adapted for flight. But it has a tail. If you look at which modern birds just have a nubbin, the tail's used to nubbin, and it has teeth. Right? So modern birds have a beak without teeth. During development, you can actually see evidence of teeth starting to form and then not forming, but adults don't have teeth. Archaeopteryx have teeth like any good dinosaur would. Okay? So the point here is that these transitional forms, they do preserve characteristics that, some of which are found in one group and other characteristics which are more primitive. Okay? This would be examples just such of an organism. But they also occur at a particular time. Right? This species occurs in the Jurassic. Importantly, we did not find Archaeopteryx in the Cambrian. We did not find Archaeopteryx in rocks that were 1 billion years old. We didn't find Archaeopteryx in the Quaternary. We found it in a period of time where we know that, where it should have occurred based on other fossils. We know this is where we had a lot of dinosaurs that had some feathers, that had a lot of characteristics of modern birds. It occurs at the right time, and its closest relatives are the right sort. So it's not only the fact that these transitional forms have characteristics that unite them with several different groups, but they occur at the right time, which is something a lot of people forget about. Whales are another good example. I mentioned them earlier. They're a real enigma for a long time because it wasn't clear to whom they're most closely related. Molecular phylogenetics came around. They said, you know what, whales look like they're artiodactyls. That is to say, things closely related to hippos and pigs and cows. Okay, you can see whales at the very top of that tree. But until molecular phylogeny came around, until we could actually sequence DNA, it was not clear where whales were, who whales were most closely related to. Interestingly, after the molecular phylogeny came around, people started to discover more early whales in Pakistan, which is not an easy place to collect fossils, and also in Egypt. And they found these, so for instance, there's Basilosaurus. Some of these whales had hind limbs. Okay? So the important point with this is that now that you have hind limbs, you can have the bones in the hind limbs are things you can actually study. What you see here is the hind limb of one of these early whales on the left and a modern artiodactyl in the middle. The point being that these whales that they found had hind limbs that had a very characteristic ankle joint that you only find in artiodactyls, the so-called double pulley astragalus. So once again, you have these early whales that have some of the characteristics such as hind limbs. It was clear that their ancestors must have walked around on land. But the modern whales no longer have hind limbs where you can actually see bones. When they found these whales with hind limbs, they had the characteristics we would have expected, and they occurred at the right time. Not in the Cambrian, not in the Cretaceous, but in the Eocene, about when we expected them to evolve based on other evidence. So that's all I want to say here. Next lecture is a visiting lecture.